Welcome back, students. In this last lecture on entropy, we're going to go over a few remaining topics that we didn't have time to discuss in the first two lectures that we had on entropy. So our goals for today are going to be to calculate the entropy for substances at non-standard pressures and temperatures. We'll see how to calculate the entropy for a chemical reaction. We're already pretty familiar with this. And then we're going to use state functions to derive the total differential of entropy, like we've done for internal energy and enthalpy. This lecture is going to be entirely on the board, so let's get to it. Our goal with entropy in this chemistry class is ultimately to apply it to chemical reactions. Just like for enthalpies of formation, we remember that there are a large list of molar entropies in the back of chemistry textbooks. Where do these values come from? At the end of the last lecture, we calculated the absolute molar entropies for substances at any temperature. We need a standard state to list the entropies at. And this standard state will allow us to know exactly what number we're looking at, what it means when we look it up in the book. Entropy varies more strongly with pressure than volume. So for this reason, a pressure of 1 bar is chosen at the standard state. And we can define a standard state as 298 Kelvin and 1 bar. And the numbers you would look up in the back of the textbook are at this temperature and pressure. What if we need an entropy at a different pressure that is not 1 bar? In the first lecture on entropy, we discussed how to calculate the entropy for an ideal gas. We found out that the delta S was equal to negative NR natural log of P final over P initial. And so that means what we're calculating is often going to be a molar entropy, which is going to be the entropy divided by N. So we take the N out and get our change in molar entropy is equal to negative R natural log of P final over P initial. So how do we calculate this for any pressure? We simply assume that our initial pressure is our standard state pressure, which is 1 bar. And then that initial entropy is already known. So the entropy at any pressure that's not the standard state pressure is equal to the standard state molar entropy at a pressure of 1 bar. And then we subtract our natural log of the final pressure that we're interested in, which in this case is just P under our notation here. And then we divide that by the standard state pressure, which is 1 bar. So we could just leave that out. If our pressure is in units of bars, if it's some other units, we do have to account for that. And this will tell us how the entropy changes as a function of pressure. You can see that if this pressure is larger than 1 bar, this natural log of this number will be a positive number and we'll be subtracting. So our entropy will go down at higher pressures, which makes more sense because high pressure is a low volume scenario usually, and low volume means less disorder and then therefore less entropy. We can also calculate the entropy for a reaction, and we do this in the same way that we did before. So our notation for this for enthalpy was that the change in entropy for a reaction is simply equal to the sum of nu I and then our molar entropies for all of our substances. And remember that this nu here is the stoichiometric coefficient for a chemical reaction, and it is negative for reactants. So if we have a reaction that is A plus 2B goes to C, to calculate the change in entropy for that, we simply need to know the molar entropy of a substance C, and then we subtract the molar entropy of substance A, and then 2 times the molar entropy of substance B. So while all entropies must be positive, delta S's, change in enthalpies for reactions, do not have to be positive because they are sums of different values of entropy. So we can have negative changes in entropy, although we can never have a negative entropy. So all of these numbers are positive. They're also all non-zero. So you may remember that the delta H naught of formation for a pure element, say oxygen, was equal to 0. That is not true for entropy. So the standard entropy of formation of oxygen is a real number, and it is non-zero because oxygen has some entropy associated with it. There's no enthalpy of formation for elements in their standard state, but there is an entropy for all of these substances. So you have to keep that in mind when we go through and solve problems. If we want to calculate the entropy of the reaction at a different pressure, we can use this equation up here. If we want to calculate the entropy of a reaction at a different temperature, we simply have to integrate. So our delta S naught of our reaction at some temperature that is not the standard pressure of 298.15 is equal to the delta S naught of reaction at our standard temperature. So I'll put 298.15 in here. And then we add the equation for changing the entropies. Just like for the heat capacity in general, we can, we can integrate using a delta Cp. So we have our delta Cp as a function of T over T dt. And in this case, this delta Cp has the same form as this equation up here. So delta Cp is equal to the sum of all of the individual heat capacities. And with this, we can get an estimation for the entropy of a reaction, or the change in entropy for a reaction at some other temperature that's not 298.15, if that is our desire. The last thing we'll do today is come up with the total differential for entropy as a function of volume. So like we talked about before, these state functions vary on pressure, temperature, and volume. So we could have entropy as a function of temperature and volume, or entropy as a function of temperature and pressure. We always have temperature because entropy varies strongly with temperature, so it's easier to describe in that way. But depending on the situation we have at hand, we could either use volume or pressure to describe the entropy. This is unlike enthalpy and internal energy that very naturally went with volume or pressure and volume. Here, entropy can kind of go with both. So what we'll do today in the lecture is describe the entropy as a function of temperature and volume, and then in class and on the homework, you'll go over entropy as a function of temperature and pressure. We can go through that example and then do it again on the homework. So we start at the same point that we always do. And again, remember, the purpose of this is not to make you guys do math and torture you with math. The purpose of this is we want to describe how entropy is changing as a function of temperature and volume for systems that are not ideal gases based on experimental parameters that we can actually measure. So that is the goal, and that is what we're looking for. And the math here is to show you that you can do this. The math is challenging, but if you're guided through it, we can get through it and figure out these answers for ourselves and kind of peek under the hood of the universe and see how the universe works. So our total differential for entropy is as follows, just like it has been before. We'll say that ds is equal to the partial derivative of s with respect to t at constant v times dt, so the rate of change of entropy of temperature times the extent of temperature change. And then we have the second term, so the partial derivative of s with respect to v at constant t dv. How can we get simpler terms for these? Well, we'll start at an interesting place, and we'll start with the total differential for internal energy. So we have du is equal to dq plus dw. If this is a reversible process, we know that dq is equal to t ds, and this comes from the fact that dq reversible over t is equal to ds, so therefore dq reversible is equal to t ds. And then we've been working with work for a while, so the reversible work is minus p dv. So we have du equals tds minus p dv. We're going to rearrange this to solve for ds to equate it with this up here. So in doing so, we'll have t ds is equal to du plus p dv, and then we'll divide by t to get ds is equal to 1 over t du plus p over t dv. What we're going to do now is substitute in the total differential for du. So in addition to being equal to tds minus pdv, we know that du is equal to cv dt, and then plus the partial derivative of internal energy with respect to volume at constant temperature times dv. So we'll substitute in this guy here for du, And for ds, then, that gets us ds is equal to 1 over t times cv dt plus the partial derivative of internal energy with respect to volume at constant temperature dv. And then we add plus p over t dv. So we can rearrange this to group the dv's together, and we end up with the following. We get that ds is equal to cv over t dt. And then here we have plus 1 over t times the partial derivative of u with respect to volume at constant temperature plus the pressure dB. If we compare this expression for ds with our initial expression for ds, we find that we have expressions for ds dt at constant v and ds dv at constant t. So we have that the partial derivative of entropy with respect to temperature at constant volume is simply equal to cv over t. And this is something that we can measure experimentally. We know the temperature, we can measure the heat capacity, and we can figure out then what ds dt at constant v is. However, our second term, ds dv at constant t, is equal to 1 over t times the partial derivative of internal energy with respect to volume at constant temperature plus the pressure. So this guy is not something that we can get an easy measurement for. We can't just measure this partial derivative in the lab. So how can we figure out what this partial derivative ds dv at constant t is? And just like most of these things in this derivation, the answer, the path to go is probably not obvious to you, but hopefully if I tell you what it is and how to do it, you should be able to follow our way through it. So what we're going to do is actually take the mixed partial derivative of each of these things. And we can do that because these end up being equal to each other. That's the usefulness there. So what we're going to do is take the partial derivative with respect to volume of ds dt at constant v. So we have this mixed partial derivative where we're taking the partial derivative of s with respect to t at constant volume, and then we're taking it with respect to v at constant temperature. And we do this because this is equal to the reverse of this. So if we first take the volume derivative and then take the temperature derivative, these two are equal since we're just taking two derivatives. So we can do this and get answers for what they are. We'll start by evaluating this term here. And so what we need to do is take the volume derivative of the entropy after we've already taken the temperature derivative of it. And so what we'll do is evaluate this. Now, we'll note that what we have, our ds dt at constant v, is equal to cv over t. So we could say that this is equal to the volume derivative of cv over t. But we're going to do something that's actually a little bit tricky here. So instead of evaluating cv over t, we're going to evaluate something different. So we're going to take the volume derivative, not of cv over t, but of 1 over t times the partial derivative of internal energy with respect to temperature at constant volume. Now, we'll see the reasoning for this when we finish this derivation, but of course, cv is equal to du dt at constant v. So we haven't done anything too crazy here. And in this case, the temperature is not a function of volume. So we can say that this is simply equal to 1 over the temperature times the volume derivative of internal energy after we've taken the temperature derivative of internal energy. So here we have 1 over t times the mixed partial derivative of internal energy with respect to volume and temperature. And that's the key. We're going to have this term pop up in the other set as well, and that's why we've written it in this way. So when we take this second mixed partial derivative, we're taking the partial derivative with respect to temperature of the entropy after we've already taken the volume derivative. What do we get? Well, we have this relatively bad expression for ds dv at constant t. And so what we're going to do then is we need to take the temperature derivative of it. So we're taking the temperature derivative of 1 over t times du dv at constant t plus p. So how do we go about solving this? Let's evaluate it. we're going to simply use the product rule. And I need another bracket in here. So what we're going to do is take the partial derivative of the respective temperature of 1 over t, and then we're going to multiply that by this second term here, and then reverse that. So using the product rule, we have derivative with respect to temperature is equal to the first component times the derivative of the second. And the derivative of this second component here is the partial derivative with respect to temperature of the partial derivative of internal energy with respect to volume. Here, so we have this mixed partial derivative, and then for p, we simply have dp dt at constant v. And then we'll have to add back in the second term, which is the partial derivative of internal energy with respect to volume at constant temperature plus p, times the derivative of 1 over t with respect to t, and that is, of course, minus 1 over t squared. It's a simple derivative that we can do. And now we've evaluated this. So we'll go ahead and put this all together. And what we end up with is the following. So we have 1 over t times the partial derivative of temperature and then of du after we've done the partial derivative with respect to volume. And then we have plus 1 over t dp dt at constant v minus 1 over t squared du dv at constant t plus p. And so we can now set these equal to each other, because remember our starting point is that this mixed partial derivative is equal to this mixed partial derivative. So this mess over here is equal to this up here. And so we can set these two things equal to each other. I'm missing my u. So in this case, we can start doing some cancellations. Here we have the mixed partial derivative of internal energy with respect to temperature and volume times 1 over t. And on this side, we also have the mixed partial derivative of internal energy with respect to temperature and volume times 1 over t. So these two terms will cancel. They are equal, just like our entropy mixed partial derivatives are equal. And so in that case, we end up with 0 is equal to 1 over t times the partial derivative of pressure with respect to temperature at constant volume minus 1 over t squared times the partial derivative of internal energy with respect to volume at constant temperature plus p. So we can do some rearranging here. I will multiply both sides of this by t squared and add this term over. So if I do that, I end up with the following. I have that the change in internal energy with respect to volume at constant temperature plus p is equal to t times dp dt at constant v. And this is almost in a form that we recognize. Before, we simply stated that the change in internal energy with respect to volume at constant temperature was equal to t times the partial derivative of pressure with respect to temperature at constant volume minus the pressure. And here we can see exactly where that expression comes from. We needed to use the total differential of entropy, but we came up with this expression for the internal pressure that we've used before. Now we can plug this back in, because remember the goal of this, again, is not to do bad math, but it's to solve for these state functions in terms of things that we can calculate in the lab. We can go back in and solve for what ds dv is. So we had ds dv at constant t. Initially, we said that was equal to 1 over t times the pressure plus du dv at constant t. Here we now have solved for what du dv at constant t is in terms of things that we can measure. So we can go ahead and substitute this in. We get 1 over t times p plus t times dp dt at constant v minus p. Our p's cancel, our t's cancel, and we get that ds dv at constant t is equal to dp dt at constant v. And this is something that we can measure. We've seen before that this is equal to our beta over kappa, where these two are things that we can actually go and measure in the lab. And that is the whole point of what we've been doing. So how does entropy change as a function of temperature and volume? We can say that ds is equal to, and initially we said that it was equal to ds dt at constant v dt plus ds dv at constant t dv. And now we've solved for what these are. So it's also equal to cv over t dt plus beta over kappa dV. So the heat capacity, beta, kappa, and temperature are all things we can measure in the lab. So we can figure out how the entropy changes as a function of temperature and volume. And of course, if we actually want to get a delta S, we need to integrate. So from this, delta S is equal to the integral of CV over T dt plus the integral of beta over kappa dP. And this will allow us to calculate a delta S as a change of temperature and volume. On the homework and in class, we'll go through how to do the same thing for pressure. We won't do that here in the lectures. Obviously, the starting point is going to be very similar. So we'll say that ds is equal to the partial derivative of entropy with respect to temperature at constant pressure, dt, and then plus the change in entropy with respect to pressure at constant temperature, dp. And I'll give the answer here. We'll go through this in class and on the homework. The answer that we get is that the change in entropy is equal to Cp over T dt minus V beta dP. So we'll go through this in class. Here we'll conclude for our entropy chapter. We saw that entropy and the second law of thermodynamics can be used to determine the direction of spontaneous change for any process. Entropy is always increasing in a natural process. We can never have a decrease in entropy, so the entropy of the universe is always increasing. We can calculate absolute entropies as compared to things like absolute internal energies and enthalpies, which we don't calculate, using the third law of thermodynamics. And we can use entropy as a state function. Typically, we'll do this as a function based on temperature and pressure, but you could do any variables depending on the problem at hand. So where we're going from here is we are going to want to continue investigating spontaneity. So here we've decided that entropy and the second law of thermodynamics determine spontaneity. In the back of your mind, you probably think to yourself, I've always used the Gibbs free energy to determine spontaneity. And that's where we're going to go in the next lecture. We're going to investigate the Gibbs free energy and see how it comes out of entropy and the Clausius inequality. And then we'll be working with Gibbs free energy and the equilibrium constant moving forward.